Hey, Algebra 2, moving on to Lesson 5. We're going to extend what we've learned in Lesson 4 to just a little bit further. We're just going to, not to a little bit further, we're going to extend it a little bit further. First of all, to get our mind in the right sort of mindset, let's look at the opening exercise. Suppose that a group of 360 workers pool their money buying a single lottery ticket every day with the understanding that if any ticket is a winning ticket, the group will split the winnings evenly, and they will donate any leftover money to the local high school. Using this strategy, if the group wins $1,000, how much money will be donated to the school? So if I just look at it, I've got $1,000. That is $2 times 360 plus 280, right? So each coworker wins a whole whopping $2, and then there is 280 left over. Another really simple way to look at it is I do, 360 goes into 1,000 2 times and some change. Okay, so that's my leftover, and that's how much money each person gets. What if the winning ticket is worth $250,000? Using the same plan as in Part A, how much money will be donated to the school? So I'm just going to make a little note over here. Use my handy dandy calculator. That's an 8. So here, using the same setup as we did before, $694 for each person plus $160 left over. Cool? Sort of makes sense. Take it a step further, what if the winning ticket is worth $540,000? Do a little math. Make sure I have enough zeros. Okay, there is no remainder in this problem. So 540,000 splits up evenly. And the school doesn't get anything. Okay, each person gets $1,500 and the school receives nothing. So you'll notice we use 360 in our example because we've been talking about a rotation. 360. Okay, what you sort of see here is how many times we are rotating around the origin. So in that first example, it was $1,000. So if I would look, each person got $2. So 1, 2, and there was $280 left over. So this is 180, 270, 280. And remember, we're talking about angles. Let's see if I can make that a little bit better. That go back to the x-axis at a right angle. That was terrible. One more time. At a right angle, where this is phi. If you can tell, that is phi. Alright, that's what we're talking about today, is this right here. Alright, suppose that P is the point on the unit circle obtained from rotating the initial ray through 390. Find sine of 390 and cosine of 390. So if we look, we're taking our initial ray and we're rotating it 360, and what's left, if I have 390 minus 360, 30 degrees left. So that's why we have our reference angle at 30 degrees. So if I wanted to find sine of 390 and cosine of 390, I'm actually finding sine of 30, which is opposite over hypotenuse, and cosine of 30, which is adjacent, over hypotenuse. So I just needed to find my reference angle, which was phi. All right, I'm going to do the first one, and then I'll give you the answers to the next few, and you can check yours on your own. Okay, first I need to figure out what my reference angle is for 405. Looks like I'm going around one time, so 405 minus 360 is 45 degrees. I need to figure out what quadrant that is so I know if my answer is positive or negative. So 405, oops, pushed the wrong button. That means my circle's going around 360, and then there's 45 left over. So I'm in quadrant 1, which is cool. So I can do cosine of 45 and sine of 45 without changing any signs whatsoever. Positive and negative sign by what I mean by sine. So I know it's in quadrant 1. So cosine of 45 is square root of 2 over 2, and sine of 45 is also square root of 2 over 2. Notice I had to figure out what my reference angle was and what quadrant I was in, so I knew if my answer is positive or negative. So I'm going to push pause and do the next two. Okay, here's the first two, or sorry, number 2 and number 3. Go ahead and check them out, push pause, look through the work, and moving on. Okay, I'll try these next two. You can check my work when you're done working on them too. I'll be right back. Alright, there we go. Let's move on to the next example. Suppose that P is the point on the unit circle obtained from rotating the initial ray a negative degree. That means we're going clockwise. So we need to find our phi, our reference angle, and figure out what quadrant it is in to find our sine and cosine, right? So for this first example, we're in quadrant 3. So we have, what are we finding? We're finding sine of negative 150, which is negative sine of 30, which is negative 1/2. And then we have cosine, just put those in parentheses, of negative 150, which equals, we're in quadrant 3, negative cosine of 30, which equals negative square root of 3 over 2. Cool, let's try some examples. Okay, the first one's see which quadrant we're in. If we go negative 30 degrees, we're in quadrant 4. Our reference angle is 30. So we have cosine of negative 30, which is just plain old cosine of 30, which is square root of 3 over 2. And then sine of negative 30, which is negative sine of 30, because we're in quadrant 4, equals negative 1/2. Let's try another one. I'm going to try these 3 on my own, and you can check your work with me when we're done. Be right back. Okay, here's your next 3 examples. I figured out what quadrant I was in, I found the reference angle, and then found sine and cosine of the reference angles with the correct sign, positive, negative. Last one, I'm going to go ahead and work it. Be right back in a second. There we go. We were in quadrant 1 for that one, which was super easy, right? Okay, Okay, let's see if we can sort of get together what we've talked about into sort of a nice, easy method to solve each of these. Let's talk about case 1. What about the values of the sine and cosine function of other amounts of rotation that produces a terminal ray along the positive x-axis, such as 1080? Gosh, if I look at 1080, I'm going to divide by 360, and I get 3 times. 3 times exactly, so 3 rotations. If we look at it, I think that's what we show here. 1, 2, 3. I'm back at terminal, which is 0. How would we assign values to cosine of 1080 and sine of 1080? Well, we're back at the x-axis. We're back here. If you remember, cosine of things are the x values and sine of things are the y values. So if we're back at the x-axis, the cosine is going to be 1 because we are in our unit circle. Let me write that a little bit better. So cosine of 1080 is going to be 1, and sine of 1080, which is the y value, is going to be 0 because we're on the x-axis, right? So cosine is 1 and sine is 0. What if we rotated around 24,000 degrees? I'm going to divide by 360. I did it wrong. Okay, we're changing this problem. I think in the spirit of what I'm trying to teach you, I think the book made a slight mistake, because 400 turns is 144,000 degrees. But in the spirit of the question, so let's just look. If we rotated around 144,000 degrees, which is 400 turns, what is cosine of that degree and sine of that degree? It's going to be the same because we are still, our point is on the x-axis. So cosine of our value is going to be, cosine is x is 1, and sine of that value is going to be 0. Okay, I just think there's a slight mistake. So state a generalization. If theta equals n times 360 for some integer n, then cosine theta is going to be 1 and sine theta is going to be 0. Case 2, what about the values of sine and cosine for other amounts of a rotation that produce a terminal ray along the negative x-axis, such as 540? So 540, if I subtract 360 real quick, I'm at 180, so I'm over here. So cosine, which is my x value, is going to be negative 1. And sine, which is my y value, is still going to be 0. Okay, 900. That gives me 2 full turns. 1, 2, and then a half. I still end up over here. Because 900 minus 720 leaves me at 180, which is right over here. So we have cosine of our degree is negative 1 and sine of our degree is 0. Guess what we're going to do next? We're going to be in the positive y-axis and the negative y-axis. Oh, we did this, sorry, negative 1 and 0. We've got it. Case 3, what about the values of the sine and cosine function for rotations that are 90 degrees or more than a number of full turns, such as negative 360? Negative 360 ends us up, so I'm going negative 1, 2, sorry, negative 630. 3. We end up right there. So cosine of our degree, remember cosine is x, my x value here is 0, and sine of that value is y, and that's going to be 1, and that would be their generalization. Oh, and here I can say it again. Cosine was 0 and sine was 1. Case 4, what about the values of the sine and cosine function for rotations whose terminal rays lie along the negative y-axis, such as negative 810? How many times would I rotate for negative 810? I would rotate 2 times around, and I would end up on the negative y-axis. So cosine of that degree is the x value, which is still 0, and sine of that degree would be negative 1 because of where we are on the y-axis. And that would also be the generalization, which is right there. Awesome. Let theta be any real number. In the Cartesian plane, rotate the initial ray by theta degrees about the origin. Intersect the resulting terminal ray with the unit circle to get a point xy in the coordinate plane. The value of sine theta is y, the value of x theta is x. And that's what we just talked about. Let's see, what else can I tell you? The domain of the sine function is going to be all real numbers. Okay, the range of the sine function, and that's the range is the y, negative 1 to 1. The domain of the cosine function is going to be all real numbers. And the range of the cosine function is also going to be negative 1 to 1. Awesome. That's it. Good work today. I hope you enjoy the problem set. I did.